Hey everyone, and welcome to today's Explainer. Today we are going to master the hidden mechanics of TCP data transfer. If you've ever stopped and wondered how on earth massive files make it across the totally chaotic internet without a single piece of data getting lost or, scrambled, well, you're in the exact right place. We're going to demystify the precise engine that makes flawless digital communication actually possible. Okay, let's dive right into this. The absolute most fundamental concept to grasp about TCP is that it's a stream-oriented protocol. That's a huge difference from protocols that just kind of chuck whole messages over the fence and hope for the best. In TCP, the golden rule is super simple. Every byte is special. It literally treats the data you want to send as this continuous flowing stream of individual bytes, and every single one of those bytes, it gets treated like a total VIP. So here's our roadmap for the day. We'll kick things off with the TCP protocol context, define the key variables and headers, and then dive into the operational logic and formulas. From there, we'll actually visualize the data transfer sequence in action, and finally, test your knowledge with real gate exam applications. All right, moving right into Section 1, TCP protocol context. How exactly does TCP keep track of millions of these individual VIP bytes flowing through a network? To manage what is honestly a massive tracking problem, TCP assigns a totally unique 32-bit sequence number to every individual byte of the application message. Think of it like a highly specific ticket for its journey. There's literally no way 2 bytes in a connection stream will ever share the same sequence number. This invisible background tracking math is exactly what's happening every single time you seamlessly load a web page or stream a video. But hey, we obviously don't send bytes one by one, right? That would be incredibly inefficient. Instead, we group them into segments. But before we send anything, we have to define our shipping constraints, which brings us to the maximum segment size, or MSS. The MSS is the absolute maximum number of bytes that can be kept in the payload field of a single TCP segment, strictly excluding the TCP header size, by the way. Knowing your MSS is absolutely vital because it completely dictates the math for the entire data transfer process. Let's transition into Section 2, Key Variables and Headers. Now we're going to examine the specific checkpoints in our digital shipping and receiving facility. So the crucial point here is how these two sides, the sender and receiver, actually mirror each other. The sender rigorously tracks what it's doing with variables like last byte written, last byte sent, and last byte act. It absolutely needs to know exactly what has gone out the door. On the flip side, the receiver buffer is eagerly tracking what it wants next. The most critical variable here is next byte expected. The receiver is constantly, and honestly, maybe a little demandingly, telling the sender, okay, I got the last batch. Now send me this specific sequence number next. Okay, moving to Section 3, Operational Logic and Formulas. It is time to look under the hood and watch this engine actually run. Let's just walk chronologically through the math here. When TCP wants to transmit a segment, it first fills the payload with up to MSS bytes. Next, it stamps the TCP header with a sequence number, which is calculated simply as last byte sent plus 1. Then, it sets the acknowledgement number to whatever it expects to receive next. And finally, the sender updates its last byte sent variable by adding the MSS to it. That way, it's perfectly locked and loaded for the next batch. Now, flipping over to the receiver's perspective. When the receiver TCP gets a segment containing, say, k bytes in its payload, it springs into action. First, it stores those payload bytes safely in the receive buffer. It then mathematically updates its own variables based on what it just received and immediately fires back an acknowledgement to the sender TCP. That way, the sender knows for a fact the data arrives safely. All right, Section 4, the data transfer sequence. We've got the context, we've got the formulas, so let's actually visualize these abstract concepts executing over a live network connection. Let's look at the very first transmission in a connection. Imagine a client with an initial sequence number of 500 and an MSS of 100 bytes. Because that initial number was 500, the first byte of actual usable data is going to be 501. So the client sends its first segment. The sequence number stamped in the header is 501, and because our MSS is 100, the payload holds bytes 501 through 600. Makes perfect sense, right? Let's move on and see how this builds. For the second segment, the client doesn't just sit around waiting. It sends the next batch. The sequence seamlessly continues. The sequence number is now 601, and the payload brilliantly shifts to perfectly capture the next 100 bytes. So that's byte 601 through 700. To cap off this sequence, let's look at a third transmission. This sequence number here is 701, carrying bytes 701 through 800. Notice the totally undeniable rule happening here? The starting sequence number stamped on the TCP header always strictly matches the sequence number of the very first byte inside that specific payload. And this brilliantly illustrates how the receiver responds to all of this. The TCP server receives that first payload of bytes 501 to 600. It processes them, and then it sends back an acknowledgement segment. This segment has no payload, but it does have an ACK number of 601. This ACK 601 is proof. It proves it successfully received everything up to byte 600, and it is explicitly telling the client, hey, I'm now expecting byte 601. Okay, Section 5, Gate Exam Application. This is honestly the best part because I assure you, all this theory we just covered pays off right now. We're going to apply it to real competitive exam questions to see how examiners test these exact concepts. Take a look at this classic one-mark question from the 2004 GATE IT exam. It asks, in TCP, a unique sequence number is assigned to each, and the options are byte, word, segment, or message. Well, think back to our quote from earlier. Because TCP is a stream-oriented protocol, the answer is A, byte. Unique sequence numbers are absolutely not assigned per segment or message. They are assigned to every individual VIP byte. Let's step it up a bit with a numerical answer type question. A sender transmits two TCP segments back to back. The sequence number of the first segment is 5,000. The sequence number of the second segment is 9,000. So, what is the size of the data in bytes carried by the first segment? Take a second and think about the mathematical gap between those two consecutive sequence numbers based on that operational logic we just went over. Did you get it? The answer is 4,000 bytes. Because the sequence number dictates the very first byte in the payload. If segment 1 starts at 5,000 and segment 2 starts at 9,000, then segment 1 must have completely contained all the bytes from 5,000 right up to 8,999. So, simply subtracting the first sequence number from the second gives us the exact payload size. It's pretty elegant when you think about it. All right, let's challenge ourselves with one final, slightly more complex scenario. Consider 3 TCP segments transmitted one after another. Each segment carries 1,000 bytes of user data. If the sequence number field in the first segment is 13,000, what is the sequence number in the third segment's header? And the answer is 15,000. Let's just walk through the logic on this one. The first segment starts at 13,000 and carries 1,000 bytes. That means the second segment must start at 13,000 plus 1,000, which is 14,000. The second segment also carries 1,000 bytes, which means segment 3 has to start precisely at 14,000 plus 1,000. That lands us perfectly at 15,000. Just like that, you've completely mastered the mechanics of the TCP byte stream. You know how sequence numbers act as VIP tickets, how the MSS dictates segment size, and exactly how senders and receivers use mathematical precision to ensure data flows perfectly across the globe. But I do want to leave you with a final thought to ponder before our next explainer. We know flawless data delivery relies entirely on this sequence perfection, but networks are messy, right? So what happens to this pristine mathematical stream, and what exactly does the receiver do if a single sequence number just goes missing in transit? Think about that and keep exploring.